So, Young, you're recording, right?
Yes.
Okay. Okay. Honorable guest speakers, honorable colleagues from Reykjavik University, honorable colleagues from the Energy Institute at the Johannes Kepler University in Linz, respected guests, dear students, ladies and gentlemen. It's with great pleasure that I welcome you to the second part of this international seminar on sustainable energy engineering, jointly organized by the Reykjavik University and the Energy Institute at the Johannes Kepler University. As mentioned previously, the objective of this seminar is to see if the two institutes have complementary expertise in regard to upcoming Green Deal or Horizon Europe calls. Last week, we had a session focusing on ongoing sustainable energy projects in Central Europe, with a special focus on regional projects in Linz. Today, we will focus on projects in Iceland, in particular on the Reykjavik capital area. Oops, 1 second, I have to switch my slides as well. As discussed last week, the two metropolitan areas have similar ambitions, are located in similar locations, and face similar sustainable energy challenges. Here a picture of Linz area with the beautiful mountains in the background. And here's a picture of Reykjavik University. The city of Reykjavik is the main metropolitan area in Iceland, accounting for about 80% of the population of Iceland. Domestic electricity production in Iceland is dominated by hydropower, accounting for about 75% of the annual production. The remaining 15% of electricity originates mostly from geothermal sources. Furthermore, almost the entire heating energy comes from geothermal sources. Nevertheless, the Icelandic government has the ambitious objective to make Iceland carbon neutral by 2040. It is my pleasure to open the second part of this seminar with 8 presentations covering important topics such as sustainable development goals in Reykjavik City, decarbonizing the industry in Iceland, side products of geothermal energy in general, services for energy producers, carbon accounting, food waste reduction, and photovoltaics. Herewith, I would like to open the floor, and as a first speaker, I would like to welcome Magnus Jósefsson. He's the coordinator of research projects at Reykjavik City. So please, Magnus, feel free to share your slides. I will stop sharing, and then you can share your slides and present ongoing projects in Reykjavik. Magnus, can you hear us?
Yes, yes, I can. Yes.
Okay.
Right. Can you see my slides?
Yes, we should be able to see it right now. Yes, we can see it. If maybe you want to make it full screen, and then we can see your slides.
It is full screen now. Is it full screen for you?
Yes.
Okay. Okay, people. So, so thank you very much for allowing me, David, to make this very short presentation. So I'm Reykjavik's research program manager, and I have been in my post since very late in 2016. And I want to tell you a little bit about the projects that we have currently running in Reykjavik, and also where we are heading in the context of Horizon Europe, and in particular the 100 carbon neutral cities mission, which is part of Horizon Europe. So, so a little bit about myself. I've been here since late 2016. I have a doctorate in business and management, and I'm very interested in digital transformation, sense making in organizations, projectification of the public sector, and so on. But I'm very interested also in social sciences and sciences in general. So it's yeah, I'm quite privileged to be in this very interesting post here in Reykjavik, and looking at these very exciting opportunities with people such as yourselves. So I'm heading the city's expedition into the research and innovation, the European research and innovation space, and of course the the reasons for this and the anticipated benefits are, of course, linking Reykjavik to local and European innovation ecosystems and participating with European institutions and the Europe, institutions and organizations and municipalities, European states even, and of course European citizens to solve these common challenges. We want to be, and we feel it is necessary for us to be part of this collective sense making and problem solving. And of course, we want to experiment with innovative concepts, processes, tools, and governance models. And of course, the European Research and Innovation Projects offer so many different opportunities for this. We want to engage with citizens on this route. And of course, Reykjavik's Green Plan, which you may be familiar with, that states very specifically that no one should be left behind in Reykjavik's green transformation. So we place a very heavy emphasis on citizen engagement and citizen participation, as evidenced in Reykjavik's democracy programs, Better Reykjavik, for instance. And of course, through our proposal writing and our grants, we are supporting local entrepreneurs. We are bringing them into these European projects, and they are getting grants in some cases to develop their solutions and introduce themselves to Europe. And of course, from the perspective of knowledge and knowledge transfer, then we're getting access to some of the most prestigious institutions in Europe, such as Fraunhofer and VTT and more, and we are getting access to very good knowledge, and we're looking beyond the immediate horizon. And of course, we get access to human capital, social and relational capital, and of course, we get the funding to do interesting things. We are, of course, very keen to develop our own quadruple helix here, and we are right now in the process of instantiating the Green Plan, Reykjavik's new Green Plan, and that, of course, means that we have to build this quadruple helix, bringing together the public sector, the research institutions, the industry, and of course citizens. And this is, of course, a very abstract view, but it's quite a substantial and complex network of stakeholders. So far we have been tapping into Horizon 2020, and we have mostly been interested in Europe in a changing world. You probably are very familiar with this cluster. Smart, green and integrated transport, and secure, clean and efficient energy. But we have a broad interest. We are very open to participate in a sort of broad spectrum of projects. So far we have 4 hits. We have 4 projects that we've gained. The first one was a project called PACE, on populism and civic engagement. And that one is ongoing since 2019. Sparks is our lighthouse project. It's a 20 million euro lighthouse project, and we are a fellow city in this project. It's led by VTT in Finland, working very closely with Fraunhofer. And there are 2 lighthouse cities in Sparks and 5 fellow cities, and we are one of the fellow cities. We recently got a new cost grant, so we were founding members of a cost grant that is exploring welfare technologies and how we can develop those to assist the elderly. And then we have a brand new project called Impulse, which kicked off on the 1st of February. And this project is looking at the implementation of AI and blockchains in the public sector. So challenges related to the implementation of AI and blockchain, and how these can be utilized to develop a more robust eID authentication solutions. So of course we get these projects, and there's lots of money, and we get interesting things to do, but we also get we have developed over the past 4 years a really big network of partners all over Europe, and some of them are are very well regarded. For instance, VTT and Fraunhofer. Of course, we have Oxford University there. We're working very closely with Eurocities. We have been working with them on proposals, and so on and so forth. And this is just sort of a very, this is a very just an example of the institutions that we have been working with. And of course, we now have the capacity to both write proposals, lead proposals, and manage projects when they come. So just to give you a very quick example of the projects, then the Populism and Civic Engagement project is about understanding better the rise of populist politics in Europe and how these may impact and are impacting Europe, of course. We want to understand the causes of populism and how we should respond to them in the development of our policies. Reykjavik, of course, is in this project because we have been we are social innovators in terms of democracy, and we have been involved with trying to improve democratic processes in the city with better Reykjavik and better neighborhoods and so on and so forth for more than a decade. So we are seen as valuable partners in this project, contributing that particular knowledge and lessons learned into the policy responses. And there on the right-hand side, you can see some of the stuff that we're doing. We're carrying out historical analysis and comparative case studies, causal analysis, and so on and so forth. And the impact of this will be producing some future visions of how we should respond to populist politics in a constructive way. Some risk analysis, how we can educate citizens in terms of the challenges that are really associated with populist politics, and so on and so forth. There's of course a website that you can visit to learn more about this project. The Sparks project is of course our biggest project, and this project is, as I said, it's a 20 million euro project, and we have two lighthouse cities, Espoo and Leipzig, and they of course, as goes with the lighthouse cities, they are doing particular trials with solutions for towards energy transformation. And you can see there in the picture on the right that there's a whole portfolio of different things that this project is doing. We are mostly interested we were mostly interested, should I say, in electric charging stations. But as we go deeper and deeper into the project, there's just so many things that we can do, and we're becoming more and more engaged with different aspects of it. As the project matures, we are in the second year now, and as it matures, then we will be looking at the uptake of different solutions that have then been trialed in the two lighthouse cities. So it really is about the fellow cities scaling up some of the things and trialing them in different contexts. The COST project, as I said, it's about synthesizing and improving existing knowledge from local, regional, national and international settings, and really understanding how we can better utilize and develop welfare technologies to assist those that need, primarily, of course, to stay at home and enable them to access services more efficiently, and really to enable them to be more self-sufficient. It's a very interesting project. It's still in the early days. It started, I think it's around 6 months ago, and we're very much looking forward to developing some grant applications on the back of this. And as you probably know, then these cost actions are about developing consortium and developing partnerships and really sort of to develop good ideas that then can be developed into grants and research and innovation. Finally, our Impulse project, there we are looking at the application of and the challenges associated with AI and blockchains, and we are doing this in the context of developing new EID or authentication solutions. We are going to work we are going to bolt this onto the Better Reykjavik platform. So, and the way we're going to do it is that we are going to develop it in such a way that it will enable disabled people who are to authenticate more easily onto our democracy platform, probably and primarily through face recognition technology. And of course, because AI and blockchains, these are universal technologies, so it's very hard to say how they will develop or what they will produce. It's very important that we understand better what they mean, what the implication of, or what the implementation of these technologies mean for the public sector in terms of risks and other things as well. So we're looking forward to that. It's still very early days in this project. So the way that we think about this is that that on the right-hand side we have the societal challenges clusters, and you can see how these projects link onto the how they draw on different calls or different subclusters from the overall societal challenges cluster. And on the left-hand side we have Reykjavik's policies, and we really try to understand the value proposition of each project, not just directly in terms of, you know, an energy project being relevant only to energy transformation, but it has a wide value proposition across the board. You know, there are educational elements in it, and there are innovative elements in it, and so on and so forth. So you can see there how the populism project and the impulse project, of course, are ICT driven projects and democracy driven projects, but they also contribute across Reykjavik's policy spectrum. And the same goes for Sparks, of course. You know, it's relevant to transport and services, but also to innovation, ICT and democracy. These projects all have a co-creation, social citizen participation element to them. And then again, you know, the cost project as well, the same applies. So policy alignment is very important to us. And when you come to us with a proposal for a project, then it's important that we are able to align your project and what it will produce to what we want to see happening through our implementation in policy. And of course, the overarching agenda is Reykjavik's commitment to become climate neutral by 2040, and of course Reykjavik's new green plan as the sort of the catalyst for this. So very quickly, what's on our boiler at the moment? On our boiler is of course Pillar 2 in Horizon Europe, particularly interested in climate, energy and mobility. Also culture, creativity and inclusive society. We already have the drafts and we are looking at them right now. And we will be assembling our resources, trusted partners to write proposals. We're also interested in food, bioeconomy, natural resources and so on. So we have a broad interest in these calls again, and we are very open to participate in projects that have that can demonstrate that they are of value to us and that will further and escalate the implementation of the Green Plan and our commitment to become climate neutral by 2040. The missions, of course, you may be familiar with them. These are huge, these are mega projects. We are working very hard now, gathering all our resources and our strength, because we want to become tier 3 cities in a mission. Tier 3 means that we are a city that is a leading city in the mission program. And of course, you may or you may not be familiar with the missions, but you can see there on the left, this is from the report on the missions, and you can see that the calls or the should I say the dimensions within each mission is, you know, it's quite varied. It concerns construction material, what we are building, how, why, and where, and so on. Real estate, the environment, of course, energy transformation and energy. Food security, mobility, of course, but it also has a very interesting aspect, which is the behavioral sector and the sort of a social science dimension to it. So we're very interested in that as well, because of course, ultimately, to achieve, climate action goals means that we have to somehow get people to think differently and behave differently. So thank you very much. I wish I could tell you more, but of course, anybody interested can reach out to me. There's my email, and I have time for a couple of questions if that's what you want to do, David. Thank you.
Thank you, Magnus. Thank you for this really inspiring talk, and which gives a beautiful overview over the activities ongoing in Reykjavik. I think we can give all Magnus a virtual applause. Thank you very much. Magnus, I think we have to stick a bit to the time. I would like to have a podium discussion afterwards, but simply not to lose too much time, I would like to go on right on with the next speaker.
David?
Gudrun, yes?
Sorry to interrupt you. I would really appreciate if we come to a bit more interactive, maybe seminar, but maybe just one comment from my side, if it's possible.
Okay, a very short question. It's simply because we have 8 talkers, and if we overtake by 5 minutes for each one, then we'll take a long time. But go ahead.
Additional remark to Magnus. Thanks a lot for your presentation. I'd just like to to say I appreciate quite a lot your approaches in social innovation. I just want to mention we have two Horizon projects on the start, both with us as consortium lead, where we really focus on social innovation. First is about citizen engagement, where we will implement 9 citizen action labs across the EU. Second one about lifestyle effects of households with more or less 30 project partners. So I will pass on your contacts to my colleagues who will run these projects, that they can start a communication with you to find maybe some common interesting facts or projects on this. So thanks a lot for this.
Thank you, Robert. I think you're going to be in contact with each other, which is great. Then I would like to give the floor to Gudrun, who will talk about decarbonizing the industry. We had a similar talk about Linz, so also there are lots of synergies that can be perhaps identified. Gudrun, the floor is yours.
Well, thank you, David, for arranging this seminar. I hope we can find some synergies for future collaboration. And I think from the presentation from last week, it should be possible because you are focusing on similar things, but not necessarily the same things. So it could be complementary. But I'm going to talk about some activities that we have on decarbonizing industrial processes. Because we know that our modern lifestyle is in many ways based on material use, and that the increasing size of the global middle class has caused or is still causing an increase in demand for materials. For example, the use of aluminium, which is one of the biggest industries in Iceland, has increased by is now 260% as compared to the year 2000. So it has not quite tripled, but more than doubled in these 2 decades. Recycling of aluminium supplies around 25% of that demand, and the rest is supplied with primary production. And we know that if we are to reach the Paris Agreement goals of below 2 degrees or even 1.5 degree temperature increase, carbon neutrality by mid-century is required. And how can the industry contribute to that? If we look at what are the sources of greenhouse gas emissions globally, we can see that energy, as in electricity, heat, and transport, is around 50%, and shifting to green energy, such as electricity, transportation, heat, this is half of the cake. And shifting to green energy, such as renewables, has been a big focus of research efforts pushing towards decarbonizing the energy production. Then we have agriculture, buildings, and a contribution here of more than 20% that is directly from industrial processes, such as the biggest contributors are steel production, cement production, but we also have aluminium production and other fertilizer, different production processes. And here we are talking about direct emissions. The energy needed to run these processes is not included in this slice of cake that we have here of 21%. They are included here in the blue cake. And there are people are working on this, but still there are not many processes that are actually solutions that have reached industrial scale to reduce those industry emissions. In our work, we have been focusing on aluminium and silicon production because those processes are operated in Iceland, and actually they are consuming about 70% of the electric power produced in the country today. Now, metals, as we know, they are always oxidized in nature. We cannot find them in the metallic form. The only exception would be maybe gold and iron from meteor cores, but in general, you will not find them as in the metallic shape. They are oxides, sometimes sulfides, but we really need to remove the element which is bound to the metallic atom in order to get the metal that we can use for the different products. So we find the metallic oxide as an ore, typically, and we need to separate the oxygen from the metal. And ideally, we could separate it in the form of oxygen, but in reality, often we will have to go through a process that actually releases the oxygen in the form of CO2 or carbon monoxide. And that is just due to the nature of the chemical processes that are used. And in addition, we need a lot of energy because being an oxide is a much lower energy state for the metallic atom to be in. So we need to add this energy often as in the form of electricity, and then we need to remove the oxygen, and that often occurs in the form of CO2. And then we have the metal that we can use for different things. Now, aluminium electrolysis occurs in big electrolysis cells. You have the raw material in form of Al2O3, aluminium oxide, and you have anodes sticking into the electrolysis cell. You pass DC current through. The metal is reduced to, the aluminium is reduced to metal, which accumulates on the bottom of the cell, and the oxygen combines with the carbon anodes and is released as CO2. One of the solutions that we and other people are working on is actually replacing these carbon anodes with inert anodes so that we could release oxygen rather than CO2. CO2 emissions from this electrolysis process itself is around 1.5 kilogram of CO2 per kilogram aluminium, but totally from the process itself is around 4 kilograms of CO2 per kilogram of aluminium when we include the production of the alumina raw materials and the anodes. And then, of course, we have casting and transport also to take into account. But as a matter of fact, as we are using so much electric energy in this process, this electrolysis process, the indirect emissions that occur when we produce the electric power to drive the process is the biggest contributor to the carbon footprint. So if we are producing aluminium with hydropower, for example, the total emissions would be around 4 kilograms of CO2, including all the different processes that lead up towards the electrolysis step. If it is produced with natural gas, the footprint is close to 12 kilograms of CO2 per kilogram of aluminum. But if we are using coal thermal power, we are at around 18 and even up to 20 kilograms of CO2 per kilogram of aluminium. So basically, it is the energy component which dominates if we don't have renewable power. And we see that the increase in production since the year 2000, it has more than doubled the production of aluminium in this period. Most of that increase in production has happened in China, where they are using 90% coal-based power for aluminium production. the smelters are located in regions where the power is mostly from coal thermal power plants. So because of that, the increase in the carbon footprint is around 3 kilograms per kilogram of aluminium. It is basically the increase in carbon footprint is double the electrolysis step. But it is this electrolysis step. Now in Iceland, we are producing the aluminium with either hydropower or geothermal power. So we are here in this emission category. And the only part of the carbon footprint that where we have any control over is this electrolysis step. And therefore, it is important for us to focus on that. We are producing so much aluminium here per capita that this is actually a big part of the emissions, CO2 emissions that come from or that occur in Iceland, even though it's a part of the ETS system and isn't the direct responsibility of the Icelandic government. It is still, something that we need to focus on. So how can we reduce the emissions? To attack the electrolysis-related emissions, the alternatives are either capturing the CO2 from the flue gases that come from those cells and doing something with those emissions, for example, pumping them into the ground using the carbon process to turn them into minerals, or we can go for inert anodes. And then globally, the most important part is to shift production to low carbon energy resources. Now this is only 40% of the average carbon footprint, and this is 70% of the average carbon footprint. But still, this is what happens within our boundaries, within our borders, where we have some control over the emissions. So it makes sense to do research in that field in Iceland. If you look at silicon production, it is not an electrochemical process. It's not electrolysis. It's a carbothermic process. And basically you put the raw materials, which is quartz or silicon dioxide and carbon, into the furnace, and then you heat up the insides of the furnace with electric current, partly through an electric arc, heat it up to 2000 degrees centigrade. This is the minimum here in the lower parts of the furnace. We need to get silicon metal out of the furnace. And the CO2 emissions from this production is around 4.7 kilograms of CO2 per kilogram of silicon, mostly due to this stoichiometry here of the reactions that happen. So basically, we increase the temperature high enough so that it is more energetically feasible for the oxygen to combine with carbon and leave the silicon behind to form a metallic phase. That's the definition of a carbothermic process. It just happens. It happens spontaneously at high enough temperature. And the power consumption here is a little bit lower than for aluminium, but still considerable. In the case of silicon, as in the case for aluminium, the production volume globally has increased by more than double since 2000. 240% is the production volume today as compared to the year 2000. And as in the case for aluminum, most of this has happened in China. The production increase has occurred there mostly. And as a result of this, the average carbon footprint of the silicon has been increasing, but not as dramatically as for aluminium. And the reason is that a significant part of the silicon production in China is on hydropower. And it's almost half of all the energy that goes into the silicon production process. And that is probably because the silicon smelters, they are smaller units. They can be paired with a reasonably sized hydropower plant. And also, if you cannot run the hydropower plant always, and sometimes you need to cut power. The silicon smelter can live with that without damaging the equipment too much. But anyways, since the year 2000, the average carbon footprint from this process has increased around 1.5 ton CO2 per ton of silicon. So there, and now about half of all the of the total carbon footprint is the energy production. So how can we reduce the emissions from silicon production? We can use biocarbon reductants. So replace coal with biocarbon, charcoal. We can use carbon capture and sequestration. Actually, it is more feasible for silicon than for aluminium because the concentration of CO2 is larger in the flue gases. It's around 4%. So we can use off-the-shelf technology to actually up-concentrate CO2 for further processing. And then we can dramatically change the process, use methane as a reductant or maybe electrolysis. And then we have the energy-related emissions. Currently, even though we have a significant amount of renewables used in the silicon production process, still half of the CO2 or the carbon footprint comes from the energy production. So shifting to low carbon energy sources is important, be they renewable or nuclear. So this is about the ratios in the carbon footprint. Now, carbon capture and sequestration. I saw that at least Marta Rose was in the audience from Reykjavik Energy. So Reykjavik Energy along with the researchers from the University of Iceland, have developed a method to make CO2 turn into minerals. And they do that by taking they have demonstrated this for a geothermal power plant, taking the non-condensable gases, which is CO2 and H2S, dissolving them in water, pumping it down to a high enough, big enough depth for the pressure to keep the gases dissolved in the water, and then they will basically react with minerals in the basaltic rock underground and form carbonates, turn into rock basically. And this is permanent sequestering of the CO2. It's basically out of the way permanently. It's very unlikely it will get out from this form. So I think most Icelanders are quite proud of this initiative. But anyways, this will not only work for CO2 from geothermal power plants. It's a great opportunity for the industry, and therefore it makes sense to investigate how we can actually take the CO2 emissions from the smelters and make them make the concentration high enough so that we can use this method. In the case of a silicon smelter, the CO2 concentration in the off gas is 4%, and you have industrial scales amine absorption units that can up concentrate the CO2 content up to a high enough value to use in this method. But of course, it's a big investment and many challenges that have to be solved for that to become reality. In the case of aluminium, it is a bigger challenge because the concentration in the aluminium flue gas is below 1%, And there we would basically need to up-concentrate the flue gas in the smelters to higher than 4%. And this requires significant R&D because it will affect the production process itself. The heat balance of the cell is very sensitive to all changes. We have so basically we have been seeking European funding led by Reykjavik Energy to go into R&D in this direction, but we have not been successful yet. One proposal has gone in, but in the meantime we have sought Icelandic funding, and we got some funding from the Climate Fund, but we are seeking more funding to continue the work. We currently have a master student and a PhD student working on thermal modeling of the cell and the superstructure, so that we can estimate which changes have to be made on the cell operation and the superstructure design in order for it to be able to cope with a reduced flow rate of by 75%, the flow rate from the cell. Then there is the initiative of inert anodes, so aluminium production with inert anodes. There we have replaced the carbon anodes with inert anodes, so that we would be producing oxygen directly. And this has been the holy grail of this industry for decades, or for 100 years, I would say, but has not been successful. But recently there has been a breakthrough with a modified electrolyte, which allows lower temperature, which makes the chemical erosion of the electrolyte on the anodes. Okay, sorry about that. That was my dog helping me with the presentation. Yeah, so a modified electrolyte has made this seem more doable. And there are several development initiatives ongoing. The best known one is the ELYSIS process, where Rio Tinto, Alcoa, Apple, and the Canadian government are leading an initiative in Canada. Rusal also has a project ongoing focusing on this, and we have also an Icelandic project, the Arctus project, where the Innovation Center has basically been leading the R&D work, but Reykjavik University has also participated, and we have had students working on this. And now we have funding from the Alcoa Foundation and the Icelandic Research Fund, focusing on some fundamental mechanisms for this inert anode project. So we have a postdoc and a PhD student working on this. So thank you for your attention, and if there are any questions, I would be happy to answer. I could also have talked about geothermal energy, but that was...
Thank you, Gudrun. I think it was a very nice overview. Maybe time for a short question, just so that we keep in time. Anyone who would like to ask a short question? I think there are lots of synergies with the project that Johannes Linddorfer presented last week, decarbonizing the industry in Austria is also a big issue that the Energy Institute in Linz is working on. In the meantime, Halldor, maybe you can prepare your slides, but if there's a question, or Robert, if you would like to comment, feel free to do so while we are putting up the slides of the next presenter.
So was everything crystal clear?
I think there are a lot of things to discuss, and I look forward to maybe perhaps setting up a special meeting on decarbonizing the industry with interested partners. but I think you presented it very clear, and but there are still a lot of questions to be answered, of course.
Okay, thank you for the opportunity to present, David.
Halldor, are you ready?
I'm ready. So can you see my screen?
Not yet. You have to share the slides.
Okay, so okay, has it appeared now?
Yes.
Should have. Okay, so thank you very much, David, for arranging this seminar and giving me the opportunity of having this small talk. I am a professor at the engineering department at Reykjavik University, and I have been working with the R&D Center at the Blue Lagoon for about 15 years. So in this talk, I'm not going to focus on a specific project, but more about the general aspect and the concept of the Blue Lagoon. So this is a photograph of the area. The Blue Lagoon itself is rather close to the coastline. It's about 15 kilometers away, and the lava is very porous, so we get seawater percolating through the lava, and where it gets mixed with the meteoric water. And that is the origin of the Blue Lagoon. So the power plant that we actually arrived from, HS Orka, is here on this picture. It was erected a few decades ago. And the Blue Lagoon was actually formed due to its activity. So this brine had too high salinity to be used directly for district thermal heating. So it was used with a heat exchanger. And then they had to get rid of the used water. And they just pumped it into the lava, but the water was saturated with silica that soon clogged the lava, so it formed a pond. The R&D center is very close to the power plant, and the Blue Lagoon itself, this spa is in this circle here. And since recently, there has also been erected 5-star hotels close to this. And there, in addition, there is this Blue Lagoon clinic where people can get the treatment for psoriasis. So this is a schematic presentations of the origin of the water. So the boreholes are about 2 kilometers long. And at that depth, we have a temperature about 240 degrees. And the seawater percolating through the porous lava get mixed with fresh meteoric water. And this gives a mixture of 70% seawater and a 30% freshwater. And this is referred to as geothermal seawater. And this is actually used, the steam from this mixture is used for electrical production. And the liquid remaining is used with heat exchanger to produce hot water for district heating. So there are both thermal and electrical power. Now the Blue Lagoon, due to its origin, has the concept of fully utilizing all the resources coming from this geothermal origin. So make full use of geothermal resources in harmony with nature. That's the concept. And the R&D center has the role of finding new products and trying to get more and more fully use of all the resources. And for the case of a historic region, the Blue Lagoon was selected 9 years ago by the National Geography as one of the 25 wonders of the world. And that is due to the well, the nature of the water. This peeling power was discovered early in the history of the Blue Lagoon. People started bathing in this, and they found out that this mixture of this silica and the salt, and also later algae that was found in the environment, created a very healthy liquid for the skin. And that was the origin of the Blue Lagoon. It was meant as a clinical treatment to start with. And that was about, well, roughly 20 years ago. Well, closer to 30 years ago, I think. The main elements that we are using in the Blue Lagoon is the silica that gets dissolved from the bedrock due to this high temperature. And then we have this salt, this mineral coming from the seawater. And this is getting mixed with algae that thrives in the nature in the nearby lava, in the nearby lava. And this all create a unique mixture. And this has been the origin of a large skincare production of the Blue Lagoon. So it has been clinically proven, and it has been published in many papers, that this has a beneficial effect for the skin. And it has also been patented. So the use of this silica that is found in the lava, found in the seawater, and also this use of the algae has been patented. That was about 15 and 10 years ago. And like I said, this effect of skin has been proven in many clinical studies. And here we have an examples of papers published in that. Actually, this clinical studies has not been in my areas. I have been more focusing on the silica itself and the algae and the chemical use of the algae. So these three main ingredients, active ingredients, are now being used to produce high value end product, the skincare line. This is not a complete line, but this is an example of the skincare product now being produced by the Blue Lagoon. But they are all using these active ingredients. So like I said, this geothermal seawater is giving this minerals, and this seawater is precipitated with silica. And we harness the silica in special tanks. And we also have this geothermal salt, which we get from the liquid after the silica has been harvested. And we use this geothermal seawater to cultivate microalgae. And in this relation, I also want to mention that this microalgae is fed on gas coming from the power plant. So although this power plant is producing green energy, it also involves release of a large amount of carbon dioxide, a greenhouse gas. The power capacity of the power plant is about 60 to 80 megawatts electrical. And I don't remember the exact number for the thermal power, but it is on similar order or somewhat higher. And this involves emission of about 60 to 80,000 tons of carbon dioxide every year. And we are taking this, just small part of this exhaust gas to feed the microalgae, because this microalgae, it's a photosynthetic microorganism. So we can convert this extract gas into this bioactive product, this microalgae that is being used in the cosmetic product. So we are getting a fully closed circle. And this is actually a unique concept, that we are just turning completely geothermal waste and other geothermal resources into this high value skincares. Now this is showing the facility we have there. So we have hot water coming into this precipitation tanks, and upon cooling, the silica precipitates. So then the silica is pumped into filter press just to squeeze out all liquids of it, and the remaining liquids is then used with thermal exchanger and boiled, leaving salt. And this salt is an important and active ingredient in the skincare, but it is also being used as a table salt produced by the Blue Lagoon. And then also part of the liquid that is remaining after the salt production is used as a cultivation media for the algae. So we are taking full use of all the resources. And here we have a photograph of the photobioreactor. So we are pumping this saline water, this geothermal brine, and this algae. It's an organism that was isolated from the area of the Blue Lagoon, so it has got adopted to this environment. So it is thermophilic. It needs about 40 degrees to grow, and we use artificial lighting, LED diodes, that is being powered by the green power from the geothermal power plant. And this emission, this carbon dioxide emission, is pumped into this photobioreactor. And that is more or less all we need. We get some nitrogen and a little bit of phosphor. Actually, we need more than this. We need also to add some nutrient, this nitrogen and phosphorus nutrient, but we are working on extracting this nutrient from a lava powder. That is one of the projects we are now working on. And I might mention in this relation that we have been developing methods to extract blue colorant from this algae. This algae is actually blue-green algae, so-called. It means that it contains both blue pigment, it's an organic protein, and a chlorophyll, a green part. And we can, by using this geothermal silica, we can extract the powder from a ruptured cell. And this gives a beautiful blue color. And we are hoping to use this blue colorant later on in some of the Blue Lagoon products. So here we have just a pure powder. It has been freeze-dried and dialyzed. And before dialyzing, we have a lot of salt as well. And hopefully we can add this to some soft drinks or even these cosmetic products, because it has also been shown that it has it improves a barrier of the skin, so, and it's also antioxidant, so it can be taken as a nutrient as well. So just to summarize the full circle, we get this water, we get this pond, this Blue Lagoon, and those of you who have been there, you may recognize the white powder on the bottom of the Blue Lagoon, which is this precipitated silica. And it is very popular just to smear it on your face and your skin. Then we have these cosmetic products, we have this salt, and also not mentioned here, but we are also using powdered this lava and mixed with this silica to give more scrubbing effect. This is also being produced. One of these cosmetic products contain powdered lava as a scrubbing material. And this picture here just demonstrate the circle. We are this echo circle from the origin of the water and the full use of the circle in the closed harmony. When we use the water on all thermal stages, we produce electricity, we produce heat by heat exchanger. We use the effluent to form the lagoon. We use the water then to get the silica, the salt. We use it to cultivate algae, and then the emission from the power plant is used as a feed material for the algae. So this is a completely closed circle, and we get these cosmetic products out of this line. So with this slide, I want to conclude my presentation. I will be very happy to answer some questions later on, but David will decide on that. So thank you very much.
Thank you, Halldor. I think we have time for a short question, just to keep up with the time. Marta Ross, meanwhile, maybe you can prepare your slides. You will be the next speaker. Will be Marta Ross. She's the Director of Research and Development at Halldor Svavarsson. But anyone would like to ask a question, please feel free to do so now.
I was not in presentation mode. David, was it? I was just seeing the.
I think it was okay. I think at least on my screen it was in presentation mode.
Okay. I saw in the chat. Yeah.
Yes.
You were in the presenter mode, I think.
I was okay.
Yes.
Good.
Yeah, I want to point out that. Okay, Johannes, please. The microphone is yours.
No, thank you. Thanks a lot for the nice presentation. I will definitely keep an eye out for the silica products in any case. Concerning my question, so the tube photobioreactor you showed, can you give us or me a rough estimate on the scale? Is it a pilot, a demo, or industrial plant?
Well, it is sufficient for all our need, but the volume is about 4 cubic meters, the total volume.
Okay.
So it depends on what kind of industry you are thinking of. I think most people would call it pilot scale, but this is more than we need. The amount of the algae is quite small in percentage, so it is quite active, and the dry material is only a small fraction of the total weight.
Do you have any kind of additional valorization pathways that you look at on the residuals? So you were presenting quite a lot, let's say, on the high value chemicals that you want to extract, and is there any kind of looking at the residual fractions?
Well, like I said, we have been concentrating more on high value end products. So we have been in the luxury position of not thinking of, what should I say, more economical aspect, but the algae in particular, it could have, of course, been used for fuel production, making biofuel and as a fish feed. But that is a very low priced market. But this, in many cases where people are only using some active ingredient in the algae extracted, then they can use the residual part in fish feed and even some other, even press oil out of that.
Okay.
But we don't need it. Like I said, we are in the luxury of having very high value end products.
Halldor and Johannes, I will provide the contact. So I think this is a very interesting discussion, worthwhile to have, of course, but we will move on with the next presenter. Marta Ross Karlsdóttir from OnPower will present ongoing research at the Halldor Svavarsson power plant and with geothermal energy. Marta, feel free, the floor is yours.
Thank you, David. So nice to be here with you today to be able to present what we at OnPower have been working on in terms of these innovative and sustainable projects. It's very nice to follow Halldor because we are working with similar concepts as HS Orka has been doing and has been pioneering at their power plant with increasing the sustainable utilization of geothermal resources. And we are following the same methodology as well at our power plants in the Hengill volcanic region close to Reykjavik. So I'm the managing director of natural resources and innovation at ON, and I'm gonna share with you some insights on my company. We are owned by Reykjavik Energy, which is maybe a name you know. It's our kind of it's our mother company, and it's been in operation for decades in various forms, but has over a century-long experience with operating utilities and energy production for the Reykjavik capital area and other municipalities. We were divided up into different companies in 2014 after new EU regulations on dividing monopolistic companies and competitive markets. So ON Power is on the competitive market side. We are producing electricity and selling directly to our customers, to homes, businesses, and industries in Iceland. And we are also producing hot water in kind of this wholesale agreement with our sister company, Veitur. And Veitur is then the monopolistic side of our operations at Reykjavik Energy, owning the utilities, the distribution systems of cold water, hot water, and electricity, and also the sewage system. And we sell them a part of our production in form of hot water to be distributed as district heating for the Reykjavik capital area. And then our newest sister is the Carbfix company. It's building upon the research project and then showing in full scale or demonstration mode the application of the Carbfix method of mineralizing CO2 in basaltic rocks, which Gudrun mentioned a bit earlier. And the fourth company is Gagnaveita Reykjavíkur, which is a data fiber optic network company, owns and operates fiber optic networks and constructs those utilities. At ON Power, we focus on producing electricity and hot water, and we are geothermal experts. We operate two fairly large geothermal power plants at the Hengill volcanic region, which is roughly 25-30 kilometers away from the Reykjavik city. Hellisheiðarvirkjun is the one that you see on this figure. It is one of the biggest geothermal power plants in the world, with 303 megawatts of installed electric power. And recently we've scaled up to 200 megawatts of thermal capacity. And for the future, we foresee that we can increase that up to 400 megawatts. And this is just expanding as the needs of the city expand in terms of heat demand for district heating. To the north of Hellisheiði, on the other side of the Hengill volcano, is the Nesjavellir power plant. It's smaller in terms of electric capacity, but larger in terms of thermal energy production. We also own a small hydropower plant with a capacity of roughly 8 megawatts. The examples I want to give you today are from different origins. I want to talk a little bit about the geothermal park, which is a similar concept as HS Orka is working with, an industrial symbiosis with combining the value streams of geothermal energy to other industrial processes. And also we have a small test facility at our power plant that is considered for R&D. I'm going to talk a little bit about the Carbfix abatement of geothermal gases that is in operation at Hellisheiði power plant, and then some projects on decarbonizing transport sector. So if we start with the geothermal park, it is this industrial symbiosis concept and circular economy concept that we are working with there. And this is a simplified schematic of the Hellisheiði plant. If we look at our resource, if I can get that, yeah. So we get a mixture of steam water and geothermal gases from our production wells at Hellisheiði. And this mixture is fed from the resource and up to the surface via our boreholes, and then towards the power plant, where they are divided into the steam and gas phase that drives the electrical turbines for production of electricity. We get an accumulation of gases, non-condensable gases, that we have to release from the energy production circle and dispose of them. And then the hot water coming from the wells is used for the hot water production. The schematic is actually a little bit more complicated than this. We're operating in 2 pressure stages at Hellisheiði, so we are maximizing the electrical capacity of the plant by producing more steam from the fluid. But in its simplest form, this is how we do it. So electricity and hot water are our primary products that we sell or send off to the utilities in Reykjavik. And the electricity is, of course, sold all around the country. But the carbon dioxide and all the geothermal gases that accumulate in this process will have to be disposed of by some means, and that's where the CarbFix project came into operation at Hellisheiði. So it was a joint research project between Reykjavik Energy and University of Iceland and other partners, and has showcased that it is possible to mineralize CO2 by mixing it with affluent water from the power plant and re-injecting it into these basaltic rock formations, where they are mineralized. Over 90% of the gas has been mineralized after only 2 years of this process. So it's a revolutionary method of carbon capture and storage, and we call it carbon capture and mineral storage, CCMS. But today we also have extra or affluent of CO2 and other geothermal gases. So we have not scaled up this technology to full reinjection of all of our CO2. But the geothermal park is then building upon the concept of utilizing waste streams from the geothermal plant, and also utilizing the main products, which are electricity and hot water. So we are seeking for partners who can utilize one or more of these affluent streams, and of course the main streams as well, to form these circular economy activity of utilizing better what the research has given us. What we have is a vast amount of organized land. So this is a picture taken showing from the Hellisheiði plant and towards the organized land that we have available for the industrial park. And we already have a local plan for the park, and there are already some activities that have been built on this site. We have restraints. We cannot offer anyone who wants to join us to be a part of the geothermal park, because we are located in beautiful scenery, delicate nature, and close to protected groundwater streams. So there's no tolerance for polluting industries in this area. So we have to be really innovative and careful in which partners we associate us with. And that is, gives us a fairly tight frame of cooperating partners that we want to welcome to our site. But we have found a few. Here's an example of those who are affiliated with the Geothermal Park today. And I want to just discuss a few of them with you, just for quick examples. So the Vaxa company, Vaxa, formerly Algae Innovation, is a algae producer, producing algae or microalgae for mainly fish feeds. But they want to develop into other businesses or areas as well as they grow. So they are using electricity as a source as a light source for the algae production. They're using some amount of fresh water that we can supply at the geothermal park, and they're utilizing waste heat from the geothermal plant as a heat source. And we hope to be able to supply them with carbon dioxide, as Halldor was discussing in his lecture before. They need CO2 to grow, but we have a different kind of gas stream than HS Orca has. We have fairly large amounts of H2S in our geothermal gas, and we are developing methods on how to clean the CO2 so it can be usable in these kind of processes in the future. But that is a challenging task, and I will tell you a little bit about that later on. But that's our future goal, is to be able to provide CO2 for clean CO2 that has been rid of the H2S following it. Climeworks is another company that we're very proud of having in our geothermal park. It's capturing CO2 directly from air. So it's capturing excessive or just CO2 from atmosphere with these large fans, and they have some membrane technology to isolate the CO2 from atmospheric levels. And then they're coupled with the Carfix methods to mix the CO2 with water and re-eject it into the basaltic rock at this Hellisheiði site. So this is a cooperation between Climeworks, between Carfix and OnPower. And they use electricity, cold water, and also affluent heat, geothermal water from our power plant, and the Carfix technology. We have also ambitions for, the geothermal park is maybe an park for or area of cooperation with developed technologies that are able to come build their structures and their production plants, and are paying customers, as you say, and are paying for these resources. But we have test facilities as well for these partners to come and test out their production in cooperation with us. And then especially to test if they can use our effluent streams in terms of gases, steam, cold water, hot water at different temperatures, and so on. So this is where you see is a dedicated space close to Hellisheiði, or on the Hellisheiði industrial site, where we have room for containers to come in and plug up with our effluent streams, electricity also, and hot water and cold water, to test out new technologies. And hopefully they will then grow to be a customer at the geothermal park when they have developed their production to full scale. And examples on what is then now located or being built at the technical park is what we call the burn and scrap station, where we are trying to purify CO2 from the geothermal condensate gas, and see if we can come up with a product that can be used, for example, for algae production or other uses of CO2. So this is just in design stage. It's a part of the GECKO project, which is a Horizon 2020 funded project, a very large project that has different work packages, and this is one of them. And we hope to be able to get this plant up and running next summer. So this is in the final design stage. The main challenge here is to purify the H2S from the CO2 stream and some nitrogen as well. Our biggest question mark today is how can we utilize geothermal fluid, which is an effluent from our power production, at 50 to 60 degrees. So we have quite enough of this stream at our locations, and few customers who can use it. So we are hoping to get solutions in terms of partners that can utilize this stream. It's geothermal water, it has some silica content and some dissolved gases as well. So it's not clean water, but it is a valuable stream, and our perfect match would be someone who could use this and lower the temperature before it's re-injected back into the reservoir. So the Carfix methodology, or the method, is utilized today at the Hellisheiði plant. We have managed to decrease our carbon footprint by 30% since 2014 by utilizing this method. And more maybe, or then it was more importantly, to reduce the H2S emissions, because this is the characteristic geothermal gas that you can smell at in Iceland with this sulfur rotten egg smell, and we wanted to decrease that pollution from our operations. So the Sulfix method is similar to the Carfix method. It's a co-capture basically of the Carfix method of H2S. And this is basically the same process as the Carfix. It dissolves the H2S into water and is re-injected into the basaltic rock, and there it forms pyrites or foolscald within the bedrock. And we have managed to decrease our emissions by 70 to 80% annually, and has been a huge success for us. So the next step is to increase the CO2 mineralization in our power plant. And we aim to have a 95% reduction of both those gases in 2025 for Hellisheiði plant and 2030 for the Nesjavellir plant. Here are a few pictures just showing showing some examples from the Carfix and Sulfix projects at Hellisheiði. And here you can actually see a drill bit or a drill core showing the mineralization of the calcite. You see these white spots all through the core. And this is an example of how the CO2 is actually mineralized. This is a calcite crystal, so it's basically the same form as the carbon dioxide will be mineralized in. And this is the station, we call it the air cleaning station, the current one that is reducing our footprint by 30%. And this we want to enlarge to be able to tackle 95% of our emissions. And then one of our focus area is decarbonizing the transport sector. And On has been a pioneer in providing fast charging stations around Iceland to kind of elevate and enhance the transition of from fossil fuels to electricity for EVs. And this is an ongoing project, has been ongoing since 2014, and we're constantly improving our network with both new stations, upgrading the old ones, and adding new locations as well. But maybe that's not an innovative project, it's more a commercial project, but hydrogen production is one of our innovation projects. And because maybe differently from the concept of utilizing renewable energies in Europe to produce hydrogen, because of this fluctuating nature of solar and wind, you can utilize the excess fluctuating production to produce hydrogen. We are, on the contrary, a baseload power. So geothermal produces stable baseload power all through the year. But we have, of course, a fluctuating market. So sometimes we actually have a production that is surpassing the energy need of our customers. And then we have the opportunity to produce something valuable while our customers are not buying the electricity. So at night, when there are low load hours, we can switch on the hydrogen production at Hellisheiði to utilize the resources and this stable baseload power more efficiently. So, and this is just an example of how the market may look like. So we have these fluctuating needs of electricity. We have a baseload power production at Hellisheiði, which is represented by this blue line here. So all the area below or between the baseload and the load curve is then available power or energy for hydrogen production. So we actually have an up and running hydrogen producing plant at Hellisheiði, and it's producing hydrogen at the moment. There are very few cars in Iceland operating on hydrogen, but they have just recently been getting the supply up and running again. So these cars are up and running as well on our roads. And this is a part of the Hydrogen Mobility Europe project. So we are responsible for constructing and operating the hydrogen production, while we have partners who are then buying production from us and distributing it as fuel in 2 locations in the capital or southwest corner of Iceland. And basically, the hydrogen station is located within the technical park. So it's one of these R&D projects that are situated in these test facility areas at Hellisheiði. We have plans of other renewable fuel production, for example, methane production, as David mentioned, I think last week, using then geothermal CO2 and H2 to produce methane. But the complexity of those kind of projects are that ON aims to be carbon neutral in 2030. And with these CCU or carbon capture and utilization projects, it's not really clear how you will account for the CO2 emissions. And it's actually working as quite of a hindrance in our projects and our cooperation today, because both the customer who is getting the CO2 for producing some kind of fuel is expecting to have a zero emitting fuel, while we are at the same time expecting to have a zero emitting power plant. So this is something that is quite of a challenge, is how to address these CCU partnerships. So who is responsible for the final emissions? And I know that this is an ongoing debate, and I hope to see some results of that in the recent future. So thank you, and I'm hoping for some fruitful collaboration opportunities with you guys. I think there's a lot of synergies, as David has been pointing out all through these sessions, but this was to showcase our pathway and where we are able to cooperate with all of you. Thank you.
Thank you, Marta Ross, for this really interesting and nice overview of ongoing projects at Hellisheiði Power Plant. We have time for a short question while our next speaker, Sveinn Pálmarsson, CEO of Vatnaskil, a service provider for renewable energies, will prepare his slides. So please, if anyone has a short question, feel free to ask now.
Maybe a short comment from my side. Thanks a lot for your very, very impressive presentation. I think, as you have mentioned and David has mentioned, there are plenty of possibilities for cooperations. So I'm really looking forward, even maybe working together with some legal aspects in CCU, with some hydrogen implementation, business models in geothermal usage. I think there's really plenty of possibilities. So I will really look forward, and maybe we can contact you in the next days or weeks to think about some further collaborations. So thanks again.
Thank you as well. And I maybe forgot to mention that we have very skilled personnel within our company and within the OR group who have been working with large EU-funded projects. So we are experienced in both applying for funds and working with big research grants, even being in charge of some of these projects. So and we have recently applied for innovation fund, both large scale and small scale projects. So we are up for collaboration, definitely.
Yeah, and thanks. And one additional comment from us, that we're also coordinating the Austrian flagship region for hydrogen, and also partner of the Austrian flagship region for, let's say, industrial processes. So if you would like to, I will pass on your contacts to our colleagues there. So I think there is also room for cooperation there.
Great, thank you. We will be in touch.
Okay, excellent. Thanks. Thank you very much. Marta Ross, could I ask you to stop sharing your slides so that Sveinn can prepare his slides? Thank you very much. Then Sveinn Pálmarsson, Managing Director of Vatnaskil, service provider for renewable energies. The floor is yours.
Thank you, David. So can you see my actual slides, not the presenter mode?
Yes.
The actual slides are very good. Well, it's a pleasure being here with you today and exploring the potentials of collaborative efforts. I'm going to give you a broad overview of Vatnaskil's renewable energy services that support sustainable development and utilization of energy resources. So first, briefly about Vatnaskil. Vatnaskil is a consulting firm focusing on renewable energy, resource management, environmental fields, climate change, and computational fluid dynamics. We specialize in developing numerical models of natural and man-made systems, including those listed, geothermal reservoirs, groundwater flows, surface waters, atmosphere, urban environment, and industrial processes and applications. We serve clients from the energy sector, public utilities, private industry, municipalities, and government. And we've gained nearly 40 years of experience in Iceland and around the globe. Our primary service sectors are listed here, being renewable energy, environment and climate, infrastructure and utilities, industrial processes and design. Today, I will be providing you with some insights into our renewable energy services, in particular, hydropower and geothermal energy utilization, as well as sustainable district energy. Now, we've gained significant experience in understanding complex hydrological systems and resource utilization through our extensive work in the past decades, particularly here in Iceland. During this period, there's been a substantial development in the country's utilization of renewable energy resources. So the characteristics of the water resources in Iceland can be largely derived from the volcanic geology, high annual precipitation, and large glacial ice sheets. In the volcanic region, we have most of the high temperature geothermal resources. Some of those have been already utilized. Currently, our geothermal utilization accounts for about 30% of the total energy production here in Iceland. Now, in this volcanic region, we also have many of the rivers, particularly those with large contributions from the glacial meltwater and spring flows. Those have been utilized for hydropower development, at least many of them. Now, currently, hydropower utilization accounts for about 70% of the total energy production in Iceland. Vatnaskil has participated in a wide variety of projects relating to hydropower resource development and management. We specialize in the construction of watershed scale models to provide reliable assessments of historic and near future reservoir inflows. With robust numerical modeling, Vatnaskil can simulate surface runoff processes as well as groundwater flow within watersheds utilized for hydropower production. These conditions require a physically sound modeling approach. The models are utilized in a wide range of applications, including development of long-term reservoir inflow based on historical weather series, as well as climate change forecasts. Also, we provide shorter-term forecasting of reservoir inflow for operation and management of power plants and for flood warnings. Services we provide also include assessment of water quality and sediment transport in reservoirs. Furthermore, we also apply and perform hydraulic design of hydropower structures such as spillways, iceways, and intake structures. Also, some related structures such as fishways. We provide services particularly tailored towards developers of small-scale hydropower plants. Those are normally considered plants under 10 megawatts. In Iceland and many other locations, there's a growing interest in utilizing streams for small hydro plants. Now, modeling services are tailored to the specific needs of the client within the field of hydropower resource development and management. And we do that for the entire project lifecycle, from feasibility studies to operational management. Here, we have listed some of the services typically provided at different phases in the development process. Now, power companies, they utilize our products for various reasons, including updating or refurbishing present power plants, to design new plants, negotiate energy sale prices to their clients. That could be based on long-term outlook on reservoir inflows and power production capacity. And also, they can utilize it to operate the entire power network based on short-term forecasts of reservoir inflows. Vatnaskil has participated in a wide variety of projects across the globe relating to geothermal resource development and management. This both applies to the sustainable exploitation of high and low temperature geothermal systems. Specific services provided by Vatnaskil include construction of field-wide geothermal conceptual models, well test design and analysis, resource capacity assessment, and implementation of reservoir management strategies, typically for maximizing production output and sustainability. Vatnaskil utilizes a wide range of analytical and numerical modeling tools, including simple volumetric assessment methods, more complicated lumped parameter models, and last but not least, fully dynamic three-dimensional multi-phase reservoir models. Our geothermal services, they are tailored to the specific needs of the client for the entire project lifecycle, from feasibility studies to operational management. There can be a significant overlap between the project phases in terms of the services provided. The listing here, though, gives a good indication of the work done at each stage. I wanted to tell you a little bit more about our work on the geothermal reservoirs and the modeling approaches, and the fully dynamic three-dimensional multi-phase reservoir models. They have proven to be instrumental in the sustainable development of geothermal systems. They give a good account for the geothermal exploitation and evaluation of re-injection and borehole renewal. The models improve our understanding of geothermal system characteristics. We can assess how they can be sustainably developed as measured data accumulates on operational parameters and reservoir responses. This allows for robust operational decisions, ensuring continued sustainable exploitation. On the left, we can see how geological strata is represented in a reservoir model, with inclined geothermal wells crossing the multiple layers of rock and sedimentary material. At right, however, we have some modeling results assembled. In particular, we're looking at hot convective reservoir underlying the insulating cap rock in gray color. And we have flow arrows indicated and the significant cooling of the rock outside the main reservoir. Now, exploiting geothermal reservoirs can have some impacts on the environment. It is, of course, important to ensure minimal impacts as we plan for the sustainable development of the resource itself. I'm bringing some examples here to explain that. One being, once the geothermal fluid has been utilized at the power plant, it either needs to be re-injected to the geothermal reservoir or disposed of properly. Now, the chemical composition of the fluid or its high temperature often hinders its release to surface water or shallow groundwater. This often calls for a deep groundwater injection and to ensure no impact to shallower aquifers that may be drinking water resource, or a source for sensitive wildlife. Now, modeling of this situation allows for a strategic injection of the waste fluid, minimizing the environmental impact. A completely different example is on the right, where we have air dispersion of sulfur dioxide, or H2S, from a geothermal system and power plants. And those are plants here in the vicinity of Reykjavik. And those plants, and the H2S dispersion is regulated, and health safety margin must be met in the metropolitan areas. The video here on the right shows such distribution from 2 large geothermal plants east of Reykjavik, with comparison of measured values at sampling sites in the capital area. The comparison of simulations to the measured values is very good, and this kind of modeling allows for design and evaluation of mitigating measures to fulfill regulation requirements. Our modeling and analysis on district heating networks, combined with our experience in sustainable resource utilization, forms a basis for our sustainable district energy services. Services span across the lifetime of a district energy system, from initial resource assessment to development strategies, operational management, and numerical forecasting. The integration of numerical models, which specifically address resource management and operation of district networks, can be used to streamline a variety of operational processes and management decisions, including sustainable resource utilization, investment planning, and general optimization of operation. This diagram shows the basic setup of an integrated geothermal district heating network, in such that we have 3 different models. They are working in combination. These 3 models are reservoir model, network model, and an operational model. These models interact together for optimal operational strategies in the entire system. This approach allows for the sustainable development of distribution networks with refurbishments and expansion, focusing on sustainability, deliverability, lifetime of investments, and profits. Vatnaskil has developed a more general approach to utilize multiple resource streams. Overall, we want to be able to integrate multiple energy resources and have a diversified energy utilization. This includes utilizing waste heat and all other potential resources that may serve downstream users. It is, however, important to optimize the resource utilization for efficiency and cost effectiveness. Modeling these systems, furthermore, it allows for various analysis, including exergy analysis. This may, for instance, help in planning suitable contributors and users to the overall system. Now, variable energy resources may potentially be added to these systems in the future. This includes gas, such as methane, that is captured in landfill or produced in, for example, biogas and composting plants. Vatnaskil provides multi-phase modeling services for optimizing such gas capture, as well as the gas transport to consumers. Such modeling is a comparable approach for our general assessment of greenhouse gas emissions, for example, for assessing the effectiveness of wetland reclamation efforts. For particularly convoluted problems in our renewable energy services, we have the option of providing high-resolution computational fluid dynamic analysis. Such analysis have proven to be instrumental for various applications, particularly where we may be dealing with complex multi-phase flow and heat transfer. Now, this brief overview on Vatnaskil's renewable energy services hopefully gives you some good idea on some of our modeling efforts to support sustainable development and utilization of energy resources. We have some additional information that can be obtained at our website, so take a look there, please. Well, thank you very much.
Thank you very much, Sveinn, for this very nice overview of Vatnaskil and the services that you can provide for renewable energies. I think we have time for a short question. So if anyone would like to ask a question, feel free to do so now. Meanwhile, I would like to ask the next speaker, Stefán Sveinbjörnsson from GreenFo, CEO of GreenFo, which does the carbon accounting in Iceland for different companies, to prepare his slides and share them on the screen. So please, if you have a question, feel free to unmute yourself and ask a question. So maybe I can comment. Sveinn and I, we have been participating in a Horizon 2020 project proposal, and it turned out to be very valuable to have companies that produce the energy, service providers like small companies or consulting companies like Vatnaskil is doing, and then research institution or academic institution. And this turned to be out a very valuable asset for proposals, and it's a bit the purpose of this seminar to bring together people from the energy sector, but also from the service providers as well as from the academic institutions. So I'm very happy to have Sveinn here as well included. Now, Stefán, can you hear us? I'm looking for the next presenter. So meanwhile, if anyone has a question, feel free to do so. Meanwhile, I'll try to get the next presenter ready. I don't see Stefán Sveinbjörnsson online. Can I? Stefán, can you hear us?
Stefán isn't here, but I sent you a message that I'd be stepping in to present GreenBytes instead.
Yeah, okay. Well, in principle, you were replacing Celia, but that's okay. I think we're just going to go ahead with the next presenter, CEO Renata Bade Barajas from GreenBytes. She is a former student of Reykjavik University who has started her own company in Reykjavik with the aim of reducing food waste. So please, Renata, share your slides, and the floor is yours.
Perfect, thank you. Okie dokie. Well, thank you very much for the introduction. I'll be talking about the role of reducing food waste in a world of sustainable development today. So just to kind of fast forward, all of us here know that climate change is one of the most pressing challenges that we face today. The consensus of climate change being caused by unprecedented amounts of greenhouse gases such as carbon dioxide, methane, and nitrous oxide hints at an interesting option for solutions. If humans can come together and pollute at unprecedented scales, maybe we can come together at unprecedented scales to put together solutions, which hopefully will be one of the outcomes of today, finding great collaboration and supporting many of the good projects that are working towards the sustainable development. So let's break down some of the contributors of this greenhouse gas emissions and subsequently climate change. We have the transportation industry, we have agriculture and energy, and all of these are wildly important for our survival. Like, we all need to transport and have mobility. We all need to eat, and we, in a modern world, all need to be using electricity. And we know that all of these things play a big role in our plight against climate change. And today I want to shed some light on a vastly overlooked contributor to greenhouse gas emissions that touches on all of these industries of transportation, agriculture, and energy. So that is food waste. So food waste is one of the largest contributors of greenhouse gases in the world. If it were a country, it would be the third largest contributor to greenhouse gases in the world after China and the US. Food waste is also linked to water usage, land usage, biodiversity loss, and even hunger. And food waste is widely prevalent because it occurs at every stage of the food supply chain, from farm to fork. And in a world of growing populations and increased hunger, we are constantly looking to produce more food, which oftentimes comes with added waste. And because food waste is growing, and because populations are growing and our need to feed people is growing, we suggest that besides just producing more food, that we optimize the food supply chains and optimize the way that we use the food that we already have, because a third of all food is currently going to waste. And just to hammer in how big of a problem food waste is, if you compare it to the global aviation industry, which contributes 2% of global greenhouse gas emissions, food waste contributes 3 times more greenhouse gas emissions than the global aviation industry. It contributes 6% of the global emissions in our world. And though this is a kind of overlooked topic, it hasn't gone unnoticed. One of the UN Sustainable Development Goals, specifically 12 of responsible consumption and production, has some focus on reducing food waste. In 2015, they set a goal of reducing 50% of food waste by 2030, which is a wildly ambitious goal because there are many efforts, but we haven't gotten there because every year our food waste is actually growing and growing. So that's actually where GreenBytes comes in. GreenBytes helps food retailers like restaurants and grocery stores reduce their food waste and maximize their profits by telling them how much food to order. We use artificial intelligence to predict future food consumption based on past sales, weather data, and COVID-19 statistics. We track inventory, we break down menus, and we predict this future food consumption. When a customer wants to place an order, we will make the suggestion of how much they should be ordering, and if they approve, they can click a button and it will be sent out to all of their distributors. And before I dive deeper into GreenBytes, because I know that there's lots of students on here. I used to be a student of David's, and I used to go to the University of Reykjavik, and I wanted to kind of touch on the innovation process and just kind of touch on design thinking and different approaches to innovation and what that looks like. So I think one of the best ways of finding product market fit, or just kind of problem solving in general, is this approach called design thinking. The first step of which is kind of similar to the scientific process, but it has some little startup-y tweaks. The first step is to empathize with your users, identify kind of who your audience is, who are you aiming to like service, or who are you aiming to come up with a solution for? And from there, you can define the problem. Once you understand your end users or the end people who are going to be interacting with your solution or your idea, could be your thesis, defining the problem. Once you have the problem defined, you go ahead and ideate. What are the potential solutions? Maybe have your hypothesis. And once you have an ideation, you make a prototype. You go in and you create a solution. This could be a wireframe. This could be, it could be a physical prototype. And then from there you test. You go back to the first set of users that you defined and see how that goes. And this is kind of a cyclical process that goes on and on for innovation. where you go back and you test and you see what your users think. And from there, you kind of go back and be like, okay, well, this didn't work the way that we thought it was. So let's go back to the definition area and redefine the problem, or maybe a new problem that is parallel to other things pops up, and kind of continue to ideate in this way, and continuing to ideate, prototype, test, and continuously there. And just to show kind of what this process looks like, I want to rewind to some of our earlier prototypes. We went in and we had these menu breakdowns, and we had these different user interface designs. And we went and we tested with our users and got the feedback that it looked fine, but they really wanted something simpler. In context, most of our customers are restaurant owners, so they have lots of things to do and don't really have time to be looking at this too much. So we took in the feedback of simplifying and really simplified, and then ended up with something like what we have today. And from there, so where does this lie in the scope of the Horizon 2020? There are a couple specific calls that I want to call out, specifically the Horizon CL6 2021 Farm to Fork 0112, which is the evidence-based decision-making to change social norms towards zero food waste, and the CL6 2022 0109 Research and Innovation for Food Loss and Waste Prevention and Reduction through Harmonized Measurement and Monitoring. So basically, the EU realizes that food waste is a problem that we need to be working together to solve. And if there's any interest in that or in collaboration to bring that to addressing these specific Horizon 2021 to 2027 calls, we're open to collaborating, and we have participated in a couple consortiums that have been quite good. Briefly want to touch on my team. We currently are a team of 4. We have backgrounds in science, engineering, forecasting, computer science, and more. And we also have a decade's worth of experience in the food service industry. So along with our technical backgrounds, we also have a hands-on experience of the problem that we are aiming to solve. So our next steps are to fortify the tech infrastructure, develop international sales strategy, and enter new markets. And I wanted to highlight this because this is like where we have room for collaboration. We are always working to fortify our tech infrastructure to have the biggest positive impact that we can. And in order to have the biggest positive impact that we can, we are also looking to see how we can scale the solution. And scaling the solution oftentimes comes alongside generalizing our technical infrastructure. For example, making our machine learning algorithms more global and making them more generalized. Currently, we have tested ARIMA machine learning models as well as, and we're currently using neural network models. But in the future, we're looking to build a more global model that is applicable to multiple types of food retailers. And we actually are currently working with the University of Iceland. We've partnered up with one of their professors, and they're running a applied data science course when we're working with some of the students to put together a project on different ways that machine learning can be applied to better predict future forecasts. We're also researching in the ways that design can be applied to implement and encourage sustainable behavior change, and how the area of sustainable behavior change and psychology and the implementation of that can merge. If any of this sounds interesting to you, or if you have more questions, please feel free to reach out at GreenBytes at greenbytes.is, or you can check out our website or our Instagram, rbk_greenbytes. Thank you.
Excellent talk. Thank you very much, Renata, for your presentation, and good luck with your company. If there's any question, please feel free to do so. We have now a bit more time because we had one presenter that didn't show up. So if you have a question or a comment, feel free to ask it now. Meanwhile, I would like to ask our last but certainly not least presenter, Rachel Brophy, to prepare her slides. So feel free to ask a question if you have a question, otherwise while Rachel is preparing her slides. So if there's no question, then we will go straight ahead with the last presentation. Rachel, the floor is yours.
Okay, thank you so much. So hello, my name is Rachel Brophy, and today I'm going to be talking to you about molecular dynamics of perovskite material for photovoltaics. So just to start out, I just want to get everyone on the same page. So I'm just going to give a couple definitions just to make this go a little easier. So first, what exactly is molecular dynamics? Well, it uses computer simulations to understand the physical movements of atoms and molecules. To do this, we use Newton's laws of motion equations to understand the movement of atoms and molecules and how they interact. So it's the basics for how this presentation is going to go, and then we're going to go into a little more detail of what exactly I'm working on. So to start out is just the basics of photovoltaics. So we want to talk about what exactly is a photovoltaic. So a definition is a solar cell is an electrical device that is able to convert light into electricity. And as we all know, this is known as the photovoltaic effect. And for something to be considered a solar cell, there are three main attributes that it has to have, and these will be brought up later in the presentation as well. So first is the absorption of light generating electron-hole pairs. Then, as charge carriers of opposite types, there's a separation between the electrons and the holes. These opposite types are probably positive or negative as they repel each other. And then it's the delivery of these carriers to an external circuit. So that basically means an external circuit will be connected to a light, a charging unit, or a fan, or anything you're wanting to power. If the opposite types are not there and the electron and the hole pairs are able to recombine, no work is done and we don't get any energy out of it. So that's why this is important. Next, I know this graph is very scary to look at, but I'm just going to be pointing out two major things of it. So there are 5 major types of solar cells, but again, I'm only going to look at these 2. So the first solar cell was actually introduced in 1976, and that was under the thin film category, which you can see in the arrow on the left side. And then most of today's research-based photovoltaics have an efficiency, which is, and an efficiency is a simple ratio of the amount of light put into the system and the amount of energy we get out of that system. Most of them range from about 12% to 47%. However, its average is about 21 to 30% efficiency. Now, if we're going under the emerging PV, which is the red category in that legend above, we see the emergence of perovskite solar cells. So the idea of this actually came to be in 1980. However, the first report of its use wasn't until 2013. At this point, it only had an efficiency of about 14%. However, as of 2020, it raised to about 21% efficiency. So in 7 years, it raised from 14% to 21%, making it one of the fastest and most interesting forms of photovoltaics as of today. So what exactly is a perovskite? So it's a crystal with a cubic structure of type ABX3. And just for a simple diagram of that, I'm going to stop sharing for a second so I can show you this model in real life. Okay, so if you can all see me, so I have a perovskite model right here, and there are 8 cubic units in this. Each cubic unit can be defined by this methyl ammonia, or this molecule in the middle of each one. On the ends, there are 2 different types of molecules, one on the ends and one in the middle. For my presentation, the ones on the end are going to be lead, and the ones in the middle are going to be iodine. So as you can see how this thing works, the methyl ammonia can actually move in the middle as it's spinning. And it works as different forces to create the dipole that I'll be talking about more. So this is just a basic model of it. I'm going to be showing some simulations that use this. It's going to be really fun. So I'm going to go back to my presentation real quick. Okay, so again, just to reiterate, we are talking about a MAPI structure. So in this type ABX, my A is going to be methyl ammonia, my B is going to be lead, and my X3 is going to be iodine. Okay, so how exactly does this work? Well, it's very simple to those three attributes I talked about earlier. So photon is going to kick an electron out of orbit, leaving a hole in its place. An electric field is created by the dipoles, which push the electron and the hole in opposite directions so they don't recombine, i.e. we actually get work done. This creates an electric current through an external circuit. So again, we're able to plug this in and we can just get energy this way, very similar to a varying amount of other photovoltaics. Now, the benefits of using a perovskite is that it is cheaper than regular silicone and other types of photovoltaics, and it also creates the current in its native material for free. That means there is no need for any other doping mechanisms or any junctions or anything. This molecule is able to create energy on its own. Some problems with this, which I'll go into a little more detail, is the iodine migration and deterioration during working conditions. We're going to see a couple examples of this migration, and yeah. All right, so next is the objective of my project. So we want to develop a physical model for the iodine migration using computer simulations. And then once we understand this migration, we want to try to propose solutions to prevent or reduce this iodine migration. For the methodology, all of the research is being done using the LAMPS software, which solves the equation of motion for each atom in small time steps. LAMP software is used by Sandia Lamps, located in Philadelphia, PA. We also use a software called Oviedo, which we take the output files from LAMPS, put it in Oviedo, and it helps us create an animation so we can see what happens in real time. Okay, so for this first one, this is a perfect model. So this means there are no vacancies or no defects in the model. So again, lead is going to be denoted by these red dots here. So this is lead, iodine is blue, and the methyl ammonia are these fun little dancing things in the middle that rotate. So again, think back to the model I just showed you, that real one, and this is the exact same structure that we're seeing, just on a larger scale. So you can see the movement of them. There's a polyhedral in the middle. It's just perfect structure, nothing wrong with it. So when we continue with this, we have a, oh, sorry, dropped my headphone. We have a model vacancy with recombination. So again, the colors are the same. Lead is red, iodine is blue, and a methyl ammonia is this, a bunch of colors in the middle. So I'm going to show two versions of this. This one is what we see when we first open the model. So there's a vacancy in this iodine group right here, and the iodine is moved about a unit cell over to the next group, and it's connected to a lead group. So when I press play, you're going to see a ton of movement. But what is actually happening here is that the iodine is moving and creating a chain reaction to fill this vacancy. I'm going to stop sharing one more time just to show you a zoomed in version of this. So 1 second. Okay, so here this is. All right, so we have our vacancy right here. We have the displaced iodine right here, and these two are going to be denoted by a different type of blue color. So this is more of a teal, whereas the iodine is regularly blue. That's because I want you to pay close attention to these two blue. Okay, so as I press play, you can see that the iodines start to move separately and join in with different groups until both vacancies are filled. So I'm going to play this again and do a little step-by-step of what's happening. So first we see that the iodine, they separate above and below. So this is because the iodine that was originally displaced is going into the very neighboring iodine group. But that means that there's too many iodines in that section. So a different iodine moves from that group and goes to its next neighboring group until all the vacancies are filled and the process is stable again. Once it's stable, they stay in their same spot and there is no more movement within this. All right, and one more time going back to my screen. Okay, so that's what happens with the recombination when there is a vacancy. We also inputted a grain boundary type. So it's a little hard to see with this, but a grain boundary, we created a mirrored vision. So there's a small triangle. I'm not sure if you can see my mouse, but there's a small triangle that goes in the middle of this animation that I'm going to show you. So there's little holes in this that are creating a boundary. So a grain boundary causes crystal defects, and they can alter the effects of the material. However, it is possible to be beneficial in increasing the stability and the efficiency of the material. So again, the colors are the same. Lead is red, iodine is blue, and the methyl ammonia are all the fun colors in between. So right in the middle of this grain boundary is a single iodine right here that is not close to anything. As I press play, there is a much smaller motion. This is because this one is at 5 degrees Kelvin instead of the normal working conditions, which is 300 Kelvin. You can see the movement of this iodine, which is the migration, as it tries to join into its neighboring iodine group. Once it joins this group, it is stable again, and the migration has finished. So it will go from its wrong place to the right place, basically, in very simple terms. Also, you can notice along this grain boundary, there are some other iodines that move in that same general pattern, but are not dissociated as this one was. Okay, next is the preliminary results and the physical scenarios of iodine dynamics. So first we notice that the iodine vacancies create a path for the migration of neighboring iodine atoms, which we saw in that recombination one that I showed you earlier. Next, we notice the displaced iodine tends to travel to the closest iodine group and then causes a chain reaction of iodine migration until the vacancy is filled. So it can continue creating vacancies and refilling vacancies with different iodines until the material is completely stable, which is again what we saw in that recombination model. If the displaced iodine is within 2 unit cells, so remember back to that, the building blocks I showed you, 1 unit cell is the place with the methyl ammonia in the middle. So if the iodine is within 2 unit cells, it will travel directly to the vacancy and then recombined. If it is further, it tends to do that chain of reaction. And then finally, lead vacancies do not seem to affect the stability of iodine. We've ran several trials with displacing a lead vacancy. However, it did not seem to affect any stability of the material. Finally, I would like to thank my supervisors and collaborators. You can find all of us at the nano.ru.is if you want to look into more research we're doing. We were funded by Landsverken through the Sustainability Institute and Forum, SIF, and RANIS, the Student Innovation Fund. And that's all I have for you. Thank you guys so much for listening.
Thank you very much, Rachel, for this very nice and illustrative presentation, where you could actually really show how the elements move and with the animations. This was very visual also.
Thank you.
If there are any questions, please feel free to ask. We have a bit time before we end. Please feel free to ask questions to Rachel about her master thesis.
Yeah, I have a short question. Thank you, Rachel. I'm just wondering, are you only doing the simulations, but also trying to produce such special perovskite cells at the lab, or colleagues of you? So can you design what, so in real life, can you design what you're simulating already? Yes, or is this?
Yes, we currently have collaborators that are working on that right now. I'm just working on the master's thesis at this moment, which is creating the simulations. But yes, if you go to the website, we can see collaborators that are doing that.
Okay, thank you.
Yeah.
Maybe just to comment, at the Johannes Kepler University in Linz, there's a Institute of Organic Solar Cells. Maybe there's a possibility to also do get in contact with them and see if you can exchange knowledge or information. So this could be also be an option. Yes.
I think we can try to realize that. We have also a project with them together about recycling of solar components, but maybe there's a possibility. We will see in the next weeks.
Yeah, that would be amazing.
Okay, thank you, Rachel. What I would like to do, if anyone has a general comment about the seminar about the speakers today, feel free to do so now. Otherwise, I will put a link into the chat of this video conference. It's the link to the unofficial calls for the Horizon Europe proposals for next year. It will be officialized, I think, in April. You can already take a look into it. And I would like to follow up this seminar in the coming weeks with perhaps more targeted smaller meetings where we get together and those who are interested can get together and discuss possible collaborations. But if anyone has a question or a comment to any of the speakers or any project that has been presented, feel free to do so now.
Yeah. Of course, I'd like to say thank you to all of you who have presented and who joined the seminar also from my side. I think there were quite a lot of, or an enormous amount of interesting possibilities for collaboration, for cooperation, for discussions, then I think in the next days, weeks, months and years. So thanks again.
Thank you, Robert. From my side, of course, I see also a lot of opportunities. I've been already discussing with bilaterally with some of you possible collaborations. But of course, I think that there are a lot of opportunities, especially now with the European Green Deal and the Horizon Europe calls, where we can apply together and then make our proposal stronger by showing how we can build synergies between Reykjavik University and the Energy Institute, and of course, all the other partners that have been presenting. So, anyone would like to comment?
Can I just comment, David?
Sure. Sure.
Just want to thank you very much for arranging all this. It's been very interesting, both last week and also now, and we look very much forward to further discussions as you're planning on. So, looking forward to hear from you. Thank you all.
Okay, thank you, Sven. I look forward as well. Since we have had now almost over 2 hours of presentations, I would like to close. Unless there's someone who would like to ask a question, feel free to do so now. Otherwise, I would like to close the seminar today. But of course, I will be in touch with you and I will follow up on the presentations we had today in order to see how we can take this a step further and how we can start a constructive collaboration between the partners.
Okay, thank you, David.
Okay, thank you, everyone. Have a nice afternoon and looking forward to the next discussions in regarding to future collaboration.
Okay, see you. Bye.
Thank you very much. Bye.
Thank you. Bye.